All right, let's get right into it. We're going to pull back the curtain on AI and look at the one thing, the one core engine that makes it all work: learning. I mean, how does a machine really learn anything? Well, it all boils down to a surprisingly simple but kind of tricky question. Okay, picture this. You're standing in the middle of a gigantic, foggy valley. Your mission, should you choose to accept it, is to find the absolute lowest point. Oh, and one more thing. You're blindfolded. Now, that sounds pretty much impossible, right? But believe it or not, this exact puzzle is what every single machine learning model has to solve. So this whole process of stumbling around in our foggy valley, that's what we call optimization. In the world of AI, that valley is basically a map of all the possible mistakes a model could make. And the bottom, the lowest point, that's the goal. That's the sweet spot where the error is as low as it can possibly get, and the model's predictions are on point. So whenever you hear someone say they're training an AI, what's really happening under the hood is this optimization process. The machine is just tweaking its own internal settings, its parameters, over and over and over, trying to drive that error rate down to zero. At the end of the day, learning is really just a fancy word for finding the bottom of that valley. Now, you'd probably guess that the solution to this problem is some cutting-edge, super recent invention, right? Something born out of the last few years of the AI boom. Well, here's the wild part. The basic map for our blindfolded hiker was actually drawn up more than 70 years ago. And this is it, a paper from 1951, a stochastic approximation method by Herbert, Robbins, and Monro. I know, it looks incredibly dense and academic. But trust me, hidden inside these pages is the elegant, powerful idea that is still the engine of AI today. The idea they came up with was called stochastic approximation, and its core insight is just brilliant. It says you don't need a perfect, high-resolution map of the whole valley to find the bottom. All you need is a way to take step after step based only on noisy, imperfect little hints about your immediate surroundings. Their whole groundbreaking method really just comes down to this simple three-step loop. First, feel the ground right where you're standing to see which way is down. That's checking the slope. Second, take one small step in that downhill direction. And third, just do it again and again and again. Check the slope, step down, repeat. That's it. It's an incredibly powerful and intuitive idea. So that simple little loop, it's basically the great-great-grandfather of the main algorithm we use to train almost every modern AI. But here's where things get really weird and a little counterintuitive. The modern version of this idea actually leans into the fact that making those steps a little bit noisy or messy is not a bug, it's a feature. A huge advantage, actually. See, today's workhorse is an algorithm called stochastic gradient descent, or just SGD. Now, the old school way, called gradient descent, would look at the entire data set, the whole map of the valley, to figure out the perfect next step. It's super accurate, but it's also incredibly slow. SGD, on the other hand, takes a page from Robbins-Monro's book. It just grabs a tiny, random sample of the data, a mini batch, to guess which way is downhill. It's like only feeling a tiny patch of ground before you decide where to step next. And this leads to the million-dollar question. If looking at the whole map gives you a better, more accurate sense of direction, why on earth would taking a step based on a tiny, noisy, and less accurate measurement be better? I mean, common sense says it should just get you lost, right? Well, it turns out the secret is in the noise itself. As this great quote from a discussion on Stack Exchange puts it, using these small, noisy samples makes the model kind of hop around the valley. Because of all that jittering, it can't get stuck in a really narrow, steep canyon, what we call a sharp minimum. Instead, the noise kind of bounces it out of those traps and helps it settle into a big, wide-open basin, a wider minimum. This hopping around is actually an amazing thing. It acts as a kind of self-correction, something called regularization. By being forced to find those broader valleys, the model has to learn the real, general patterns in the data instead of just memorizing the specific examples it was trained on. And that's absolutely crucial. It's what helps the model generalize and perform well when it sees new data out in the real world, avoiding a classic AI problem called overfitting. Okay, so this brings us to a really practical problem that every AI engineer faces. What's the right size for that little sample of data? This is famously known as the batch size dilemma. Let's just break it down. If you use a large batch, yeah, your sense of direction is much more accurate, but man, is it slow. You make fewer, more precise steps, and you run that risk of getting trapped in one of those sharp minima that don't perform well later. On the flip side, a small batch gives you a noisy, less accurate direction, But it's way faster, which means you can take a lot more steps in the same amount of time. And most importantly, that noise is your friend. It's what helps you find those big, wide minima that lead to a much more robust and effective model. It's a constant trade-off. But of course, the story doesn't end with just basic SGD. Over the last couple of decades, researchers have been building on this core idea, essentially trying to build a much smarter hiker. You can think of these modern optimizers as our blindfolded hiker getting some serious gear upgrades. They're still following that same core principle, always take a step downhill, but now they do it with a lot more intelligence and efficiency, almost like they have a better feel for the terrain. So let's look at a couple of popular ones. There's SGDM, which adds something called momentum. Just imagine our hiker is now more like a ball rolling downhill. It builds up speed, which helps it to smooth out its path and just power right over any small bumps or flat spots. Then you've got Atom, which is even cooler. Atom is like giving our hiker a pair of smart hiking boots that adapt to the terrain. They can take big, confident strides on flat, easy ground, but then automatically take smaller, more careful steps when the slope gets steep and tricky. Now, if you actually look at the math behind these newer optimizers, whoa, it gets complicated fast. But don't let that scare you. The fundamental goal hasn't changed one single bit since 1951. It is all about finding the bottom of that foggy valley. We're just trying to do it faster and more reliably than ever before. And this is a super active field of research. I mean, right now, some of the smartest people in AI are trying to prove that optimizers like Atom can get to the bottom even faster. They're trying to understand how they work in really bizarre valleys with constantly changing steepness. And maybe the holy grail, they're trying to design optimizers that just work right out of the box without needing a human to perfectly tune all the little settings. So let's just step back for a second and bring this all home. We've gone from a simple thought experiment all the way to the cutting edge of AI research. What's the big takeaway here? The whole story starts back in 1951 with Robbins and Monroe's brilliant idea. By the 80s and 90s, its direct descendant, SGD, was the go-to tool for training neural networks. And today, the grandkids of that original idea, these advanced optimizers like Atom, are the real engines powering the massive AI models that are literally changing our world. So when you really get down to it, the fundamental engine that drives this entire AI revolution is this beautiful, elegant 70-year-old idea. The simple, intuitive process of taking small, kind of noisy steps downhill, over and over again. From a dusty old academic paper to the most advanced technology on the planet, that core logic is still there. And that just leaves you with one final thought, doesn't it? This foundational concept from 1951 is still at the heart of AI today. It really makes you wonder, what simple, elegant idea, maybe being written up in some obscure paper right now, will be the engine that powers the world 70 years from now?